Welcome to lesson 3B, where we talk about Le Chatelier's principle and the changes in concentration. So, in the previous video, we looked at what happens to the reaction mixture when we change concentrations of different chemicals, taking the Haber-Bosch process into consideration. So let's discuss it. We have nitrogen reacting with hydrogen, 3 moles of hydrogen for every mole of nitrogen, and that forms ammonia, and this reaction mixture is in equilibrium. So if we increase the concentration of nitrogen, according to Le Chatelier's principle, the reaction that will oppose or counteract this change will be favored. So which reaction will use up the excess nitrogen? So the forward reaction is favored. To try and decrease the nitrogen concentration, so it will use up some hydrogen. So the concentration of the hydrogen will decrease and it will form more ammonia. So the concentration of ammonia will increase. Next, we need to look at the reaction rate graph. Now, please don't get a scare or a fright. I will explain it to you. So if we increase the nitrogen, now this part of the graph, the initial part of the graph, is when the reaction started initially, and after some time, so the forward reaction rate will decrease and the reverse reaction rate will increase up to a point where we have dynamic chemical equilibrium. So the solid line for the forward reaction and the broken line for the reverse reaction gets to the point where they're on top of each other. Now, what happens to the forward reaction when the concentration of nitrogen is increased? The reaction rate shoots up. The reaction becomes much faster. Now we've got more nitrogen. More nitrogen will, because it's a reversible reaction, the rate of the forward reaction will slowly but surely decrease to a point where the next dynamic equilibrium is reached. So the new equilibrium is reached at this time here. So let's say this is at time 0, and there at time t1 the first equilibrium was reached, and at time t2 the nitrogen was added, and at time t3 the new equilibrium was reached. Now to reach this new equilibrium, the rate of the reverse reaction must increase again. So the broken line also needs to go up, and where the new equilibrium is reached, the two lines are together again. Next, we need to look at the concentration graph. Now, the concentration of each reagent would be unique in every situation, depending on what they start off with. So don't get a fright, I'll explain the next graph to you. This is a concentration graph. Now, we started off with hydrogen at that concentration. What happens to hydrogen? The concentration of hydrogen drops as the forward reaction takes place. Here, at this time where the graph goes flat, T1, that is where the first equilibrium is reached. Next, we need to look at the concentration of nitrogen. We started off with that concentration of nitrogen, and the concentration of nitrogen decreases as the forward reaction takes place up to a point T1. What did we start off with when we at the T0? How much ammonia did we have? We had no ammonia in the reaction chamber. So the concentration of ammonia would increase, the rate of the reaction would increase, and the concentration of ammonia increased up to the point where the first equilibrium was established. So there the three lines are parallel, but they're not on top of each other because the concentration of each reagent would be unique to that reagent, not to say they will be equal. Now here, at that point, there was nitrogen added to the reaction. So the concentration of nitrogen went up. Okay? Then to establish the new equilibrium, the concentration, the forward reaction is favored in order to decrease the amount of ammonia. So at time T2, nitrogen was added and its concentration went up, and then it had to go down again for the reaction to reach equilibrium. What happened to the amount of hydrogen? The concentration of hydrogen just dropped in order to reach the new equilibrium. What must happen to the concentration of ammonia? Slowly but surely, because the forward reaction is favored, that reaction will take place faster and faster until we get to the time where the new dynamic equilibrium is reached. We can say that time is T3. So you need to take note of the difference between a concentration graph and a rate graph. What will happen if we decrease the concentration of nitrogen? If we decrease the concentration of nitrogen, the rate, if we have the forward reaction rate will decrease, reach equilibrium. Then if you take nitrogen out of the system, the rate of the forward reaction would drop drastically, and then it will increase in order to get to the new equilibrium. What will happen to the rate of the reverse reaction? It will increase. Sorry, I'm taking this first part. That's where the initial equilibrium was. Then the nitrogen was removed. Now the rate of the reverse reaction will also decrease. There will be less ammonia forming. The ammonia would rather decompose to form more nitrogen in the reaction mixture. And there we have a new rate of equilibrium, but it will be a lower rate because you removed the nitrogen from the reaction mixture. What will happen to the concentration of the hydrogen and the nitrogen? Let's look at that. We started off with a certain amount of hydrogen and equilibrium was reached. We started off with a certain amount of nitrogen and equilibrium was reached, and we started off with 0 ammonia and equilibrium was reached. Then at time T3, T2, the nitrogen was removed from the container. So what happens to the concentration of nitrogen? It drops. What will happen to establish the new equilibrium? The reaction concentration must increase because you removed nitrogen from the chamber, the reaction chamber. The more nitrogen needs to be formed. How can the more nitrogen be formed? By the ammonia decomposing in order to reach a new equilibrium. What will happen to the amount of hydrogen? There will be more hydrogen formed until a new equilibrium is established. Let's look at the rate graph when we remove ammonia from the reaction mixture at equilibrium. So originally, the initial equilibrium would be reached after time T1. The reverse reaction will speed up. Then at time T2, we remove ammonia from the reaction rate, so from the reaction mixture. So the reverse reaction will actually drop drastically. It will slow down a lot. And then as the hydrogen and the nitrogen reacts, it will make more ammonia again. But the new equilibrium will be at a lower rate. It will be slower. The forward reaction, because the hydrogen and nitrogen is removed as the forward reaction is favored, that reaction will slow down as time goes along to establish the new equilibrium. Right, so next we look at the concentration graph. I've cut off the first part of reaching equilibrium, so I'm looking at hydrogen, ammonia and nitrogen at equilibrium already. So the first thing that the thing that is changed here is the concentration of ammonia is decreased. So here we have the concentration of ammonia decreasing drastically as it is removed at time T1. What is going to happen to the concentration of the hydrogen? Because the forward reaction is favored, the concentration of the hydrogen will be decreased. As the forward reaction is favored, the concentration of the nitrogen will be decreased, and the amount of ammonia will increase to form a new equilibrium.